Okay guys, here we go. Let's take a look at our Polar Day 1 lesson. Much of this is a review from last year. A great deal of it is there. There will be some new material that's on the second slide, but this first slide is pretty much review. But I am going to go over these concepts again as we start into polar. First of all, if you take a look over here, plotting points in polar form, hopefully you recall how that works. Remember, the points are in this form, r theta, and here's an example up here of plotting points in polar form. Hopefully that's just a reminder. We are going to have to remember how to convert points and equations from rectangular form to polar coordinates, and these four equations are going to be pretty important to us, just like they were last year. We need to remember these four equations in order to be able to do the things that we're getting ready to work with. And also graphing. You will be expected to graph without a calculator. I certainly am not going to test you on the names of all of these polar things. You can choose to remember it or not. It probably would be to your benefit to at least know, looking at a particular equation, knowing what the graph might look like before you have to graph it without a calculator. But again, I'm not going to test you on anything like that. It's just probably to your benefit. With these ones with the petals, kind of knowing what they look like depending on how they're formatted is just helpful to you. It's not something you have to memorize. It's just helpful to you when you graph. And that's pretty much an overview of the material that we learned last year. Okay, so what we're going to do several examples of this type of material on the next slide, and then we'll talk about the derivative of polar. That would be the new thing for today, is finding the derivative. All right, so let's go to our second slide. All right, these examples over here, these first four right here, are basically going back and forth between polar and rectangular coordinate systems. First, we will do just points. We're given right here a polar point, and they want us to find the rectangular coordinates. So those four formulas on the previous slide you're going to have to remember. We will use our x equals r cosine theta and y equals r sine theta for this. So x equals, and because of the way this is ordered, we know that is r and that is theta. So x equals r, which is 7, cosine of 2 pi over 3. So we do our unit circle values, and we see where what cosine is at 2 pi over 3, which is -1/2. So 7 times -1/2, or -7/2. Our y value, the formula is y equals 7 sine theta. So we sub in our r, sine of 2 pi over 3. Again, unit circle values, pretty important here. Sine of 2 pi over 3 is root 3 over 2. And we get 7 root 3 over 2. Our coordinate point we're given here, or we calculated, is -7/2, 7 root 3 over 2. Now what I would like for you to do is double check. I always want you to double check, because whatever quadrant this point is in on polar, so we know polar has got this kind of thing going on. 7 is the number of rings, and that's positive. 2 pi over 3 is in which quadrant? It's in the second quadrant, right? So I'm supposed to have a point that's in second quadrant with a positive ring. So I'm supposed to be in here. I need to look at my rectangular point and verify that it's in the proper location. So -7/2, 7 root 3 over 2, is that going to be in the second quadrant? It is, so we have the proper point. Hopefully we remember from last year that there are an infinite number of ways to write polar points, but not an infinite number of ways to write rectangular points. So we just need to make sure that what we have found is where it's supposed to be. Also is a good double check to help you see if you've made a mistake. All right, so let's take a look, and let's go from rectangular to polar. Now we use the other two formulas, the r squared equals x squared plus y squared. So our x squared plus y squared, which is 25. So r is going to be either positive or negative 5, depending on where we want to be. Our other formula is tangent theta equals y. So tangent theta equals y over x. That is not a unit circle value. So your options would be you would either have a calculator or you might just write it as arctangent 4/3. I mean, if you didn't have a calculator, you could just write it as arctangent 4/3. So I did put it in the calculator and I got 0.927. And so let's try to figure out how to pair these together so that we're in the proper quadrant. 3, 4 would put us, in the first quadrant. So if I use well, first of all, let's work with the angle. 0.927. We know that pi is 3.14. So pi over 2 is half of that, like 1.5 something or 1.6. So 0.9 is in the first quadrant. We are in the proper quadrant with our angle. So what does that mean about our r? It has to be positive. If we're already in the proper quadrant, we need to make the r positive. So our point is going to be a positive 5 and then 0.927. Or arctangent 4/3 if you don't have a calculator. Okay, and that's just a reminder on points, changing points back and forth. Okay? Now, Well, that would also be a problem. You would have to, in order to tell for sure which quadrant it is, you really would need a calculator. Otherwise, you would just have to hope that it's in the first quadrant where it's supposed to be. All right. So let's take a look at our next ones. What we want to do here is we have equations in one format or the other, and we want to change them to the other. So on our first one, we have r equals secant theta tangent theta. Now thinking back to our 4 equations, we do have an x equals r cosine. So the first thing, let's just turn those into sines and cosines and see if we can, since we have formulas that are in sines and cosines, why don't we just turn that into sines and cosines? So secant is 1 over cosine. Tangent is sine over cosine. So that basically is sine over cosine squared. Now, one of the quickest ways to get rid of a fraction would be to do cross products, cross multiply. And that's actually what I'm going to do. I'm going to take this cosine squared and I'm going to multiply it over here. So it would be r cosine squared theta equals sine theta. Now, thinking back to the techniques that we used last year, I could square both sides, but that isn't going to help me with the sine. It's still kind of by itself. There was one technique that we used, multiplying both sides by r. I don't know if you remember that or not, but that was a technique that we would use. And that would probably be the best here, is to simply multiply both sides by r. When I do that, I get r squared cosine squared and r sine. So we know r sine theta, that's a direct translation, that's y. And what I would like for you to do is think of r squared cosine squared as r cosine times r cosine. I would like for you to think about it that way. We know with exponential rules we are allowed to do that. So r cosine times r cosine, we know r cosine is x, and r cosine, so x times x would give us an x squared. And that would be our equation. Now, I've had lots of questions today on how do we leave it, what form do we leave it in? Well, whatever its normal form is, we like to solve for y. That's what we normally do, unless it's not possible. In this case, it actually is already solved for y. But that's what our preference is, if possible, is to solve a rectangular equation for y. Unless it's a circle or something, we know we don't do that. It's just whatever normal form it's going to be in. That's how you want to leave it. If we had, if this was a circle, we would leave it in a normal circle format. X squared plus y squared equals, r squared, whatever the number is. So it's just whatever is normal for us. The next one is polar coordinates. We have an equation in rectangular coordinate form for the Cartesian coordinate system. We want to change it to polar. And again, we have a formula, x equals r cosine theta, which just sub those in. So I have 9 times x is r cosine theta and y is r sine theta. With that substitution, I do have an equation that is a polar equation. It's just not in proper form. If we can, we should solve for r. If we can. If we have r squared, I don't know if you remember from last year, typically with an r squared, we would leave the r squared. We wouldn't like square root both sides. So this is going to yield an r squared, and I'm just going to, instead of trying to solve for r, because it's r squared, I'm just going to leave the r squared in it. So r squared cosine theta sine theta equals 4/9. Now, I will tell you that your book, and probably in a multiple choice question, they might do something a little bit fancier. What does cosine times sine? It's almost a property or an identity that we know. It's almost sine 2 theta, isn't it? It's a double angle. So really, what actually your textbook does is it multiplies through by 2, multiplies everything by 2. So it can turn that into sine 2 theta. Now, if you don't go that far on a test or quiz, I'm not going to count off for it, but I just want you to know that probably it won't look like that as a multiple choice. They probably would do something else to it to make it shrink, to make it smaller. So we're going to multiply through by 2, everything by 2, and that's going to give us r squared, and 2 cosine sine is sine 2 theta equals 8/9. This would probably be how you would see it on a multiple choice. You certainly could solve for r squared and move the sine 2 theta to the other side if you wanted to. So that would be 1 over, basically if I move it over here, it's 1 over sine, right? And what could we turn 1 over sine to? Cosecant. I mean, you could. Just know that that's possible. All right. Everybody okay so far? All right, let's get to graphing. You do need to know how to graph them by hand. And what we're preparing for with our graphing is we're preparing to find area. Like the area of one petal of the flower, which we actually worked on last year, finding the starting and stopping of a petal. If you remember, if you were in Pre-Cal Pre-AP, you would have done that, found starting and stopping of a flower in preparation for finding the area of a petal. That's what we're really working on. So that's what we will be doing tomorrow or the next day. I don't remember which day. All right, so let's graph. I'm going to show you how I graph by hand. You certainly, if you learned a technique last year that worked really well for you, stay with it. I'm just going to show you what I do. I don't really like doing a T-chart with a bunch of points. I like graphing. I like making a Cartesian coordinate graph of this and using that as my T-chart. So I'll show you what I mean. I would just do a Cartesian coordinate. This is 3 plus 3 sine. So it's shifted up 3. That's where my axis is, and its amplitude is stretched by 3. It's sine, so it starts here at the axis. So we have pi over 2, pi, 3 pi over 2, and 2 pi. And so it starts here at the axis and then it goes up and then down. Okay. The reason I do this is because to plot points, I'm just going to look at this chart and I'm going to find any point that I want. I don't have to do an infinite number of points. I have an infinite number of points right here. So I start here at angle measure 0 and my ring value is a 3. So here's my axis right here. My ring value is 3. 1, 2, 3. I put a point. I go to my pi over 2 and plot a 6. These angles in between, these values in between, you certainly could do an approximation of, and if you need to refer back to it, they're there. I usually just go for the quadrantals and try to get away with just doing that. 1, 2, 3, 4, 5, 6. Hopefully we realize that between 0 and pi over 2, these are all positive ring values. It goes from 3 to 4 to 5 to 6. So, and we don't connect normally with straight lines in polar. They're normally curved. So I would just do an estimate. I really wouldn't spend a lot of time trying to make it perfect. All right. So then when we get to pi is back at 3. And so I would, again, do an estimate, because I know between pi over 2 and pi, in this section right here, all of my r values are positive. I'm in that particular quadrant. I haven't flipped to another quadrant. All right, so going to 3 pi over 2, we're at 0. Hopefully we all understand that it is not a straight line from this to this. So let's look at the space in between pi and 3 pi over 2. Okay, all of these ring values are positive. That means I am in this quadrant. I'm in the quadrant. Okay, all of these values, you know, I go from 3 to 2 to 1 to 0, so I'm going from 3 to 2 to 1 to 0. You know, it swings me around. So I would just do kind of an estimate. Then at 2 pi, I'm back to my angle measure of 0, or 2 pi. And again, I have an r value that's positive. I'm going from a ring of 0 to 1 to 2 to 3. So something like that. Okay, and that's how I prefer to graph off of a chart like this versus a T-chart. But it's totally your choice. However you want to graph is fine. I'm not going to grade you on your graphing. Okay? Now, of course, if you don't graph very well, your area is going to be messed up. Right? So it's for a purpose. We're graphing for a purpose. The new stuff is down here. This is the new stuff right here, finding the derivative. Now, I need to make this clear because earlier there was some confusion. What I'm getting ready to do is derive the formula. This formula does not change. If you want to memorize the formula, you do not have to derive it. But it's fairly complex, and that's not something that I want to commit to memory. If you want to memorize it, that's fine. But I don't have it memorized. I derive it. And I write it on my piece of paper. Whenever I'm doing derivatives of polars, it's sitting right there. I don't try to do it from memory. It's really a bad idea to try to do it from memory, unless you have a great memory. And I mean, some of you probably do have a great memory, but I don't. I need to see it. So if you recall on parametrics, for parametrics we had the dy dx, remember? And the top was dy dt and the bottom was dx dt. Remember that? It's the same kind of format, except it's dy d theta and dx d theta. Okay? Now the way that we can derive this and not have to memorize it, again, once we have the formula written here, it is the formula. It will not change. You're going to use it for no matter what your polar looks like. What we can do is we can use formulas that we already know, x equals r cosine and y equals r sine, and the product rule to get our formula. And again, this is a formula. Okay, so what I'm going to do, let's remind ourselves of the product rule, fg plus fg, first things first, second things second. Remember the good old days? Okay, here we go. That's our product formula. So I'm going to do dy d theta. Why are we using the product rule? Well, I have an r, which is a function, and I have a sine, which is a function. That's a function times a function. I have to use the product rule. So I take the derivative of the first thing, which is r. It's not a theta, so I have to tag it. So the derivative of r is 1, and I tag it dr d theta. Dr d theta. Then we copy paste the second thing, sine theta, plus, see I'm doing the product rule. We copy paste the first thing, r. We take the derivative of the second thing, The derivative of sine is cosine. And that's my numerator. If you want to commit your numerator to memory, you don't ever have to do this again. Okay? Now let's do the denominator. We're going to do dx d theta. We're going to be working with this. So we do the product rule. The derivative of r is 1 dr d theta. Copy paste the second thing, cosine. Plus, copy paste the first thing, r. The derivative of cosine is negative sine, right? Derivative of cosine is negative sine. So really, instead of putting a plus here, it would be easier for us to work with if we put a minus there. So minus r sine theta. And again, if you want to commit the denominator to memory, you'll never have to do this again. This is the formula. It will not change. That's what you will write on your paper or have in your head when you're doing derivatives of polar. Okay? But I'm always afraid that I'm going to get the numerator and denominator reversed, and maybe I'll put the negative in the wrong place or something, so I just derive it. Now we're going to use it. Notice how I need dr d theta. So I go over here. We're supposed to find dy dx and the slope of the graph at the given value, which is pi over 6. So I'm going to need dr d theta for my formula. So I'm going to take my r equation and I'm going to find dr d theta with it. So it's in the proper variables. I don't have to tag. It's got r theta, dr d theta. So dr d theta equals, the derivative of 3 is 0. The derivative of 2 sine is 2 cosine. Okay, that's my dr d theta. And everywhere in my formula that I see it, that's what I'm going to put in its place. So dy dx equals, okay, and dr d theta comes first, so 2 cosine theta. And copy that, that's sine theta, plus, now where do you think we're going to get the r from? It's given, isn't it? It's this right here. I've got to put 3 plus 2 sine theta everywhere there's a r. So 3 plus 2 sine theta, that goes in place of this r, and then cosine theta. That's my numerator. Yes, it's a big mass. These are take a while and are fairly complex to do. So you won't have a whole lot of them. Alright, now let's work on the denominator. We're going to put our dr d theta there, which is 2 cosine theta. And then there's a cosine. Minus. We're going to insert the r. And then copy the sine. Now, if your purpose is just finding a slope value, you can really just take that pi over 6 and sub it in 8 different places. Okay, my preference would be to shrink the number of times I have to do arithmetic. You guys know how I am with arithmetic. Okay, I would rather do some cleaning up of this and then sub the pi over 6 in than just jump into it. If you want to jump in and sub the pi over 6 in, go for it. But you do need to know how to simplify it in case the purpose of it is just finding the derivative. If the purpose is just finding, I can tell you that the answer choices are not going to look like this. So let's work on simplifying. I'd like to do some of this in our head. So 2 cosine sine, we know what that is, right? That's sine 2 theta. Alright, if you look over here, when I distribute this cosine, I'm going to have another 2 sine cosine. See that? That's another sine 2 theta. So I have two of them, don't I? 2 sine 2 thetas. So I have 2 sine 2 thetas. And what that does is it gets rid of this and this. Okay, I still have this cosine to distribute to the 3, so I have plus 3 cosine theta. Now what I have just accomplished is instead of having to sub in pi over 6 4 times in the numerator, now it's only twice I have to do it. Okay, now let's work on the denominator. This is 2 cosine squared, and this is minus 2 sine squared. Okay, I need you to think about that. A lot of people earlier were saying that's 1. Okay, that's not 1. What is cosine squared minus sine squared? Yeah, it's a double angle for cosine, isn't it? Cosine 2 theta. So I really have 2 of them, right? I have 2 of them. So I have 2 cosine 2 thetas. And that eliminates this one and this one. Okay, so what I have left is minus 3 sine theta. And now I have successfully gotten rid of 4 substitutions in the bottom to just 2. And that's about as simple as we can get it. So now we sub in our pi over 6. So I have 2 sine 2 times pi over 6 plus 3 cosine times pi over 6 over 2 cosine 2 times pi over 6 minus 3 sine pi over 6. Unit circle, really important. So 2 times pi over 6 is pi over 3, right? So that's 2. What is sine of pi over 3? Sine of pi over 3. Root 3 over 2. Okay, and cosine of pi over 6. Root 3 over 2. Over. Okay, we have cosine of pi over 3. 2 times, what's cosine of pi over 3? 1/2. And, oops, it's a minus. And sine of pi over 6. It's 1/2. So basically this reduces, the numerator gets me 5 root 3 over 2, right? Denominator, 2 over 2 minus 3 over 2 is negative 1/2. I fix my complex fraction and I get negative 5 root 3. When it's all is said and done, that is my slope. Okay? All right.